The final lesson in this algorithms pack is on bin packing algorithms. There are three types of bin packing algorithms that we're going to do. We're just going to do first fit, we're going to do first fit decreasing, and we're going to do full bin packing. Each one is slightly better than the previous ones. Bin packing problems is not to do with literal bins, it's to do with fitting things into things that have a certain limited number of amount of space. So it could be big containers that have a certain capacity. It could be music tracks onto a CD, cars onto a ferry are ones we're going to look at. It could be cutting things from fixed lengths, lengths of wood from a big length of wood or something like that. One of the things you may be required to find is a lower bound for the number of bins that you can fit your stuff into. All you do to work the lower bound out is you add up your total amount of stuff that you've got and divide by the total size of the bin. So for this example one here, we've got Oscar is backing up his classic film collection onto DVDs. Each of his DVDs can fit 8 hours onto it, and the length of his films are listed there. For a lower bound for the number of DVDs that he will need, all I'm going to do is add these up. And divide by the total size of the bin, which in this case is the size of the CD, which is 8 hours. Add those up, you get 23, which gives you a total bin size of 8. This will be 2.875, which means he'll need 3 CDs for his lower bound. There's a fewest number of DVDs that he'll need. No matter what you get, you always round up. So even if I'd got 2.1, I would round that up to 3, because I would still need 3 DVDs to fit on. It says, can you find an arrangement that uses this number of DVDs? Well, we're going to come back to this one later on, so we're not going to do this here. And we're going to look at 3 algorithms. The first one is the first fit bin algorithm. So let's have a look at this example 2. So this example 2 is about a service list. So it says it has a 6-ton capacity, and we need to transport a series of machines of various masses. We're going to use the first fit algorithm to determine which machines should be carried in each trip. So the first fit algorithm, literally you work your way along the list in the order that you're given them, and you fit them in the first bin available, which in this case is a trip in the lift. Okay. So the first mass is 4 tons. We can take this 4-ton machine on the first trip. The second one is 1 ton. We could fit that in the first trip as well. So we fit that in, and now we're doing a trip of 5. So we could fit another 1 in, and that's it. The next one's 2. So it won't fit in the first bin. It won't fit on the first trip. So now we need to do this 2-ton mass on the second trip. The fourth one's a 5-ton mass. It won't fit on the first trip. It won't fit on the second trip either, because it would take that up to 7 tons. So it fits on the third bin there. Next one's a 3-ton mass, so it won't fit on the first trip because we've only got space for a 1-ton machine. It will fit on the second trip though, because we've got space for a 4-ton machine, so we can fit a 3-ton machine on that second trip. Next one's a 2-ton mass, which won't fit on any of these trips. All of these trips only have 1 ton left, so our 2 now has to fit on trip 4. Our 3 again won't fit on 1, 2 or 3, but it will fit on our 4th trip with that 2. And again, we've got a space of 1 left over. We've got a 6-ton mass, which has to go on a trip on its own, which will go on trip 5. And then this 3-ton mass feels like we should be able to fit it in somewhere, but because all of these have just got a space of 1 ton, it has to go on its own trip at the end of trip 6. This has a lot of wastage. So we've got space for 1 on the first one, 1 on the second one, 1 on the third one, 1 on the 4th one, and 3 on the last one. So we've got wastage of 7 here, which feels like we should be able to have a better arrangement for it. The advantage of using first fit is that it's fast and easy, but it's usually pretty rubbish. A better method would be to still do first fit, but still put your list into order, into decreasing order. So we start with the biggest ones, fit those in first, and then we can fit the smaller ones in around it. Unless it specifically asks you to do it, you don't need to use a sorting algorithm. So you don't need to use bubble sort or quick sort on these. You can just put it in order yourself. So if I'm going to put this in descending order, I start off with 6, and then I've got 5, 4, and I've got 3 3s, 2 2s, and a 1. So I'll put it in decreasing order first. I then apply the first fit algorithm to this. So my first one is 6, and I'll do that in a trip on its own as trip 1. Then my 5-ton machine, I'll fit it in there for trip 2. My 4-ton has to go on trip 3 because it won't fit on any of those. My next 3 has to go on a trip on its own because it still won't fit on a 5 or a 4. But then I can fit another 3 on with it, and this will give me a full bin, a full trip plus trip 4, which is good. I've got another 3 which must go in a trip on its own because it won't fit in with the 5 or the 4. But then this first 2 I can slot in with the 4 to give me a full bin on trip 3. This second 2 I can slot in with this 3 in trip 5 to give me a bin of 5. And finally this 1 I can squeeze in on trip 2 to make another full bin of 6. These first 4 trips now all are full. They have a total of 6 when the maximum capacity is 6. So this one just has a wastage of 1 from the final trip. This has given us a really good solution. This will be the optimal solution. First fit decreasing still won't always give you the best solution, but it is better than first fit. Generally, the solution, the method that will give you the best fit is called full bin packing, which basically is you look at your list and you find by inspection some full bins, and then you fit the remaining items in using first fit. So back to Oscar and his DVD collection. And we're going to apply the full bin packing algorithm to fit these on 3 DVDs. So I'm looking at this list and thinking, can I match some of these decimals up to make integers that I can fit in? So the first one I'm looking at is 1.75 and 2.25, which gives me a total of 4 hours, which I could put together with these 2's to give me a total of 8 hours on DVD 1. So I made a full bin here just by observation. I'm looking at my other decimals and thinking, can I make these add up to whole numbers as well? So what I'm looking at and thinking is I could do 0.9 and 3.1, which would give me a 4. Can I get another 4 from here? Not obviously, but if I do 1.2, 1.1 and 1.7, that will also give me 4. So 1.2, 1.1, 1.7 and 0.9 and 3.1. This will give me another full bin of 8. The remaining numbers I can fit in just by first fit. So I've got 2.5, 2.5 and 2. That will fit nicely, give me 7. So this has a wastage of 1, but this is an optimal solution because I can fit it on 3 DVDs. And remember, we calculated that the lower bound earlier on was 3 DVDs. So this is what we call an optimal solution. The disadvantage of full bin is it can be really hard if you've got a big set of data, but it usually gives the best solution. The final section of this pack is on the order of an algorithm. So the order of an algorithm is to do with its efficiency. So this tells you how efficient it is in relation to the size of the problem. There's a lot of stuff here, but I'm just going to do some examples. You can do this kind of thinking about scale factors and stuff, but I prefer to use a set method that will work for all different types of questions, which I'll show you now. So this example 1 here talks about the bubble sort. So the bubble sort is an algorithm which we say is of quadratic order. This means that the time it takes, which we'll call capital T, is proportional to the number of numbers that you're sorting squared, because it's quadratic. Obviously, you can get rid of this proportion sign by putting equals kn squared. In this question, it tells us it takes 10 seconds to sort a list of 5 numbers. So this tells us that T is 10 and N is 5. So we can use this to calculate K. So I get K is 10 over 25 or 0.4. We can use this then to work out how long it'll take to do a bigger list of numbers or any other list of numbers by sticking in n is whatever. So this is asking us how long it will take to sort a list of 50 numbers. Well, I'm doing t is 0.4 times 50 squared, which will give you 1,000 seconds. You could do this using scale factors as well. So if it takes 10 seconds to sort a list of 5 numbers, to sort a list that's 10 times longer, because it's quadratic, it will be 10 squared longer. So you take 10 seconds and times it by 100 and you'll get 1,000 seconds as well. But that's not a foolproof method, whereas this one is. Later on in the course, we're going to do algorithms called Prim's and Kruskal's algorithms. So these have cubic order. This says if a computer can find a minimum spanning tree using Prim's algorithm for a graph with 20 vertices, so this is our n, in 2 minutes, which is our t. How long does it take to find the minimum spanning tree for a graph with 40 vertices? So again, if it's cubic order, it means t is proportional to n cubed, or t is the same as kn cubed. Using the information in the question, t is 2 and n is 20, we can substitute that in and we get k is 1/4,000. If we then put in this without n is 40, 1/4,000 times 40 cubed. This will take 16 minutes. Again, alternatively, you could do this using the scale factor. So we've got double the number of vertices. If it's cubic order, we need to times time by 2 cubed. So we've got 2 times 8 gives you 16. For this final example, you can't use the scale factor method, which is why I've been doing the kn squared, kn cubed method all the way through. So this one says a computer is programmed with an algorithm with an exponential order 2 to the n. That means that t is proportional to 2 to the n, or t equals k times 2 to the n. It tells us it takes 3 seconds to solve a problem of size 30. So 3 equals k times 2 to the 30, and we can work out that k is 3 times 2 to the minus 30. I'm just going to do it like that. It wants us to then estimate the time to solve a problem of size 150. So if I put in my k and I put in n is 150, this is the same as 3 times 2 to the power 120 seconds, which is a long time.